Hello, everybody. So last time we've seen that there are problems, there are languages that are not recognizable, and we did it with the accounting argument. There are just many more problems than machines that can solve them. And today we want to see a specific problem, a problem that we actually would love to solve, that is not decidable and even not recognizable. And we will start with the acceptance problem for Turing machines that we already seen, ATM. So the pairs of machines M inputs W such that M is a Turing machine that accepts the string W. The theorem is that ATM is recognizable but not decidable. And the fact that it is recognizable comes from the existence of a universal Turing machine. A universal Turing machine is just a machine that recognizes ATM. We didn't discuss yet how you construct a universal Turing machine. We'll talk about it a bit more when we will really want to see what's the complexity of a universal Turing machine at the last chapter. But intuitively, a universal Turing machine just simulates the machine M running on W. So you can put M on one tape, W on the other tape, and just simulate the running of M on W. So ATM can be recognized, but we want to see that it's not decidable. So that's the main theorem. As a conclusion, a corollary, we will show that not ATM is not even recognizable. And I'll explain why it is a corollary towards the end of this video. So we're going to see two proofs that ATM is undecidable. The first one is going to be proved by contradiction. And for anybody that gets confused out of proofs of contradictions, we'll also see a proof by a constructive proof later on. So for the sake of contradiction, let's assume that that ATM is decidable. This will mean that there is an edge that decides it. There is a machine H that decides ATM. So what does H do? H on input M and W accepts if M accepts W and rejects if M doesn't accept W. So whether or not M rejects W or just loops, H is going to reject MW. And now we want to define a new machine, D. With this machine will have only one input, which is the machine M, but it will treat M both as a machine and as a string. So essentially what it will do is run H on the pair MM. And then it will output the opposite of H. So H is going to run on MM, it always accepts or rejects, and H is going to, and D is going to output the opposite. So what do we see about D? D of M rejects if M accepts M, and accepts if M does not accept M. We just took the definition of H and we plugged in M both for the machine and also for the string W, for its input W. Now let's see, so this machine should do this thing for every machine M. Particularly, it should do the same thing also for the machine D itself. So let's see what happens when we run D on itself, on D. So plugging in D for M, we get that D of D rejects if D accepts D, and D of D accepts if D does not accept D. And this is a contradiction because D is a machine that either accepts or rejects, and each one of these two options that are the only two options leads to a contradiction. Now, these kind of arguments are called diagonalization arguments, And we'll see that the same argument exactly pictorially, just so you see where this naming diagonalization comes from. So let's draw the outputs, so a table of the outputs of H. So H has two inputs. It has an input, one input which is a machine, and the other input is a string. But we already said that every string encodes some machine, so we can just have in this table, we just call them by machines. So we have M1, M2, M3, these are the machines, and M1, M2, M3, these are the strings. And what we will care about is the diagonal, which is what D, the machine D, looks like. Now, the machine D that we described is also a machine. And therefore, there is a row in this machine that tells us what does D do. And D is also a string, so there is a column that corresponds to D as an input. Now let's see what happens. What does D do? It looks at the diagonal and it outputs the opposite. So D on M1, right, so D of X outputs the opposite of HXX, meaning that it is the opposite of the diagonal. So D on M1, look at H M1, N1, and reverse it. And similarly with the M2, M3, and M4, and so on. And this is why when we look at the row that corresponds to D, we see the opposite of the the opposite of the diagonal. So we see reject, reject, accept, accept. But now when we reach the point, we reach the row that corresponds, row and columns that correspond to D, we don't know what to put there, because we know that D is a row that is the opposite of the diagonal, but DD is on the diagonal. So in this point, we need both to put what's on the diagonal and also its reverse. So this is pictorially. I don't know if it helps you or not, but at least it may give you a sense why we call it diagonalization. Right, so D of D outputs the opposite of HDD, which is D of D. Now, as promised, let me give you a constructive proof that ATM is undecidable. So since this is a constructive proof, we will not assume that we have a machine that decides ATM, but rather that we have a machine H that recognizes ATM, and that we know we have. So H is a machine that recognizes ATM. And therefore, H, just by definition of recognizing, H of MW accepts if M accepts W, and it rejects or loops if M does not accept W. This is how you recognize, and this is what recognizing means. Recognizing means that you accept every yes instances, but you either reject or loop on every no instance. Now we're going to define a new machine, D of H, DH, as follows. DH of M runs H on MM until the simulation halts and outputs the opposite answer. In case, of course, the simulation halts. If the simulation doesn't halt, then DH just loops. It's very similar to what we had before, but now a machine H does exist. And now we have three possibilities of what can happen when we look at DH on the machine, on any machine M. It's going to reject if M accepts M, because H of MM is accept, therefore DH of M is going to reject. We output the opposite. It's going to accept if M rejects M for similar reasons. But now we have a third option. It can loop if M loops on M. Because if it simulates age of MM and it loops, the simulation doesn't end, and therefore the age doesn't output anything. Now let's see again what happens when you plug in D for M, or DH for M. And when we put all of this, we see that DH on DH rejects if it accepts if it rejects. So these two options are impossible. They lead to a contradiction. But the last option is that they loop if DH loops on DH. And this means this is equivalently if age of DH loops. And since there are only three options and the first two lead to contradiction, then the third is the only option that happens. So there is no contradiction. We just can conclude that DH must loop on DH. And this means that we have an instance DH, which is not in ATM, because if it was in ATM, then age of DH would accept, but age fails to tell us about it. So age DH runs forever. It means that if you have age that recognizes ATM, it doesn't decide. Every age that recognizes, we can find an input that makes it run forever. So kind of concluding, as we said, given a code of any machine age that recognizes ATM, we can effectively construct an instance DH where DH does not belong to ATM. So if age would decide, then age would reject it. But instead of rejecting, age runs forever on the input DH. So age, therefore, cannot decide ATM. A machine that decides ATM would give an answer always. So given any program that recognizes the acceptance problem, we can efficiently construct an input where the program hangs. And the next question is there a problem that we care about that is not recognizable? We already know that there are many problems that are not recognizable, but is there a problem that we care about that's not recognizable? We just showed a problem we care about that's not decidable, and we'll see one that's not recognizable. So let's kind of remind ourselves what's the connection between decidable and recognizable. A machine that is decidable, for every W, it says yes or no. It accepts or rejects. And it accepts or rejects exactly based on whether W is in L. Recognizing means that you say yes always if W is in L, but in case W is not in L, you may reject or loop. And other names are recursive and recursively enumerable. And the theorem that will help us deduce what we want is that L is decidable if both L and not L are recognizable, and it's if and only if. And therefore, if we believe this theorem that we'll prove in a second, then you get that ATM, and we know that ATM is recognizable but not decidable, we can conclude that not ATM is not even recognizable. Because if not ATM would have been recognizable, and then we'll have that not ATM and ATM are both recognizable, which will mean that are both decidable, which we know is not true. So let's prove the statement about recognizing and deciding. Given a language L, we have its negation, not L, and we say that L is decidable if and only if both L and not L are recognizable. So if M1 is a machine that recognizes L and M2 is a machine that recognizes not L, then I want to show a machine M that decides L. This will prove to us that if L and not L are recognizable, then L is decidable. The other side is easy. So if L is decidable, then L is definitely also recognizable. But if L is decidable, then not L is also decidable. You can convince yourself. And therefore, not L is also recognizable. How would we do this? So the machine M1 always accepts X when X is in L. The machine M2 always accepts X when X isn't in L. It means that for every X, one of these machines always halts. And no matter which machine halts, we know the answer. So if M1 halts, and then so if X is in L, M1 would halt and will accept. So we'll know that X is in L. If X is not in L, then M2 is going to halt and accept. And therefore, we know that X is not in L. So what we can do is simulate, just like in a universal Turing machine, you simulate one machine, you can simulate two in parallel, kind of simulating one step on one step on the other. You can put each one of these machines on a different tape. And you simulate them in parallel. Exactly one of the two will accept. Perhaps both of them will halt, but at least one of them will halt, and exactly one of them will accept. And again, if M1 accepts, then you can accept. If M2 accepts, you can reject. So some parting thoughts. There are two problems that we really care about that are not decidable. And one of them is not even recognizable. And I got a comment in the last survey that I look a little bit sad in the videos, and you can see that if I have such grim things to share with you, then it is understandable that sometimes I'm sad delivering the bad news. And there is more bad news coming up in the next video, so stay tuned.